Hello everyone, my name is Rouf. I'm a PhD student at York University. Today I'll be discussing our industrial paper, a framework for developing DevOps operation automation in cloud using components off the shelf. This work is done with my colleagues, Joydeep Mukherjee, who's a postdoc at York University, and Marin, who's a professor at York University. And we did this work in collaboration with IBM. We have Joe Wigglesworth and Radu Mateescu from IBM Canada. So let's get started. DevOps is a popular practice that enables the development team and operation teams to continuously coordinate and collaborate with each other. By deploying DevOps practices and tools, we can build and deploy services and applications while providing good quality of service to end users. With commercial enterprise software increasingly being deployed on the cloud, it is important to adapt DevOps principles to cloud-based applications to assure good quality of service. This leads us to our next area of focus, multi-cloud platforms. These aggregate multiple cloud providers to achieve faster, easier, and better application building and deployment. However, ensuring good quality of service in multi-clouds require a substantial level of automation and adaptation. This can be supported by MAPE-K frameworks, a very influential control loop model. The abbreviations stand for monitor, analysis, planning, and execution. The MAPE-K loop cycles through these phases and shares data through a common knowledge base. To support autonomic computing, there are existing products that follow the MAPE-K framework. Industrial MAPE-K frameworks are robust and reliable and are designed to handle production applications. However, they support limited analysis based on basic threshold-based monitoring and planning. Autonomous frameworks proposed in academia are more flexible and utilize a wider variety of analysis, including machine learning models, analytical models, control loops, etc. However, they are less robust and non-scalable, as many of them are not designed for production applications. So in our paper, we explore the feasibility of developing an autonomic MAPE-K framework for multi-cloud platforms by integrating existing services and components off the shelves, software, COTS, C-O-T-S for short. We incorporate MAPE-K into continuous deployment, as seen here in the DevOps lifecycle to support it. Continuous deployment refers to automatically releasing developer changes to the application into production. During the application deployment, the DevOps teams needs to monitor and manage their infrastructure to assure the services are provisioned and perform well. Our framework incorporates the COTS and available services to perform each of the phases in the MAPE-K loop, and the DevOps team specifies and develops the requirements that needs to be satisfied for their managed application. The development and movement of the services are then autonomously managed by our framework. So these are our established requirements for our frameworks, and I'll go through each of them one by one. The first is availability. Availability is a measure of how the system is able to run without failure and how fast it recovers from failure. And it's important for good quality of service to the end users. Services deployed in multi-cloud environments can suffer from faults, and recovering these quickly are challenging because the environment spans from multiple cloud providers, each offering different mechanisms of control and management, which can leave room for faults for these services. So we need highly reliable components that can be used in a production environment. The next is multi-cloud integration. Since each cloud providers offer different mechanisms to control its infrastructure, integrating features and services, as well as managing and automating services can be complicated. This is a requirement we need to meet to support automating services in a multi-cloud. The next requirement 3, is autonomous configuration for cloud applications. So services deployed on multi-cloud environments require an autonomic framework that is able to deploy an application on multi-clouds and then self-manage the application at runtime. So our framework needs to handle a variety of inputs from different service components to make sophisticated decisions and perform a wide variety of adaptive actions to the services at runtime. This enables better service management and allows us to optimize quality of service And we also need to be able to keep track of changes to the multi-cloud resources, which can be used for more autonomic decision-making for the services. The next requirement is scalability. We need to handle monitoring large amounts of metrics and deploy a large amount of applications across multiple servers. And we need to scale our services at runtime, and this has to be done automatically and efficiently. And requirement 5 is ease of deployment. So we need to provide the DevOps teams an autonomous framework that is easy to deploy and can be integrated with the services without incurring significant levels of development. Thus, each of the cost tools selected has to be easy to learn, configure, and implement. So based on these requirements, we answer these 3 research questions. Research question 1, is it feasible to build a MapeK framework for multi-cloud applications by integrating existing COTS and services? Research question 2, what are the challenges of building such a framework? And research question 3, what is the performance and efficiency of this framework? So research question 1 explores the COTS and available industrial services to determine if they meet our requirements. Research question 2 identifies the various tasks needed for integration and challenges we experienced. And research question 3 evaluates the frameworks on different self-adaptive use cases on a IBM benchmark application. So here, these are the main components of our proposed framework, which is the cloud monitor, which is responsible for the monitoring stage, the state rule engine, which is responsible for the analysis and planning stage, and the workflow engine responsible for the execution stage. So you can see the process in this diagram. We have the managed service on our multi-cloud environment. The metrics are streamed into our cloud monitor. The data is sent as an event to the state rule engine. This makes a decision, which is sent as a plan to the workflow engine, and the workflow engine makes the changes in the environment through commands. So let's go through each of these components in detail. So the cloud monitor distributes a cloud monitoring tool on each cloud provider and runs continuously alongside the service to collect performance metrics at runtime. We can collect the resource utilization metrics continuously at runtime at an interval of t seconds, which can be configured by the DevOps team. And then the performance metrics on the multi-cloud environment are aggregated and streamed to the state rule engine. The cloud monitor also uses service discovery to find new instances where the services are deployed. So this is done through an exporter, which exposes the performance metrics to the cloud monitor. So when a new instance is deployed, the cloud monitor can use service discovery to find that instance. And this can enable continuous automation. So when a new instance is deployed to our framework, it can automatically be monitored. So with these reasons in mind, the ability to deploy a cloud monitor on multiple cloud platforms allow the DevOps teams to enable multi-cloud integration, which supports requirement 2. The cloud monitor can automatically handle large selections of input metrics from heterogeneous cloud platforms, which supports requirement 3, which is autonomous configuration. And then the DevOps team can easily deploy the cloud monitor and can integrate it with the rest of the components in our framework, which supports requirement 5, ease of deployment. So the events from the cloud monitor are sent to the state rule engine. So the state rule engine is responsible for the analysis and planning stage of the MapeK loop. It is used to execute and manage operational rules. These rules are composed of a set of when, then rules. So when a condition occurs, then perform a consequence or actions. So these rules facilitate the autonomic decision-making and enables the DevOps teams to collaborate to maintain a desired level of quality of service at runtime in a large multi-cloud environment. The operation teams can utilize the rules to manage and deploy the infrastructure and platform for the service at runtime, while the development team can autonomously configure their application as a service on the infrastructure at runtime through the rules. So let's talk about the 2 stages in the MapeK for the state rule engine. The first is the analysis stage. We can use the when statement and validate the data from the cloud monitor. We can utilize the states of the state rule engine to define the current event of the service to make a decision. So here, let's look at a state diagram of the analysis stage of the state rule engine. So business rule 1 compares the performance metric event against a threshold value. If the metric meets or exceeds the threshold value, the state is transitioned to an initiated state. The next rule checks if the threshold is still met after a certain time period. of that initiated state. If not, the state is canceled. However, if the performance meets the threshold, which is business rule 2, it causes the state to transition to prepare for scaling. And this triggers business rule 3, which starts the planning stage and prepares a plan to scale. So for the planning stage, the service deployment and modification plans are defined in the then statement. These are configuration and deployment details of the service. This plan is then sent to the workflow engine. Using the state rule engine allows the DevOps teams the robustness to maintain the quality of service in large services spanning multiple cloud platforms by taking adaptive actions to a rule set. This supports requirement 1. Also, using the state rule engine, we can orchestrate the scaling of multiple services deployed on different cloud platforms with rules that are easy to deploy, supporting requirement 4. And this means integration in the DevOps process will be more efficient with minimal impact on the actual application, which improves ease of deployment, supporting requirement 5. So the workflow engine is responsible for the execution stage of MapeK. It uses templates, which are the infrastructure details of the service described in high-level configuration syntax. The service are then deployed by the commands issued by the workflow engine based on the template descriptions. Once the service is deployed, the workflow engine can modify and apply changes to running instances, for example, applying a new update to the service. These templates are written in infrastructure as code scripts, so we can automate DevOps operation by integrating the convenience of rules alongside infrastructure as code capabilities of the workflow engine. So for the requirements, the templates can automate service deployment in multi-cloud environments, which supports requirement 2. The templates are high-level description of the service, which makes it easy to keep track of a large number of growing services, supporting the scalability of services for requirement 4. And using infrastructure as code scripts of the workflow engine, this provides more flexibility for DevOps teams to describe, modify, and manage the service configurations at runtime, supporting requirement 5. So this brings us to research question 1. Is it feasible to develop a MapeK framework for the multi-cloud application, which it is, by reusing COTS? There is an abundance of commercial and open source services, especially for monitoring and execution components. The offerings for analysis and plannings are weaker, thus more research is needed for developing reusable services for those stages. The rule engines can also act as a language common denominator for the development and operation teams due to their low complexity but high expressiveness. So here we present the COTS we selected to build the MapeK framework. So in this table, we have COTS and other potential COTS that can be used to build the framework. The reason we chose our COTS were due to our industrial partnership with IBM and previous experience with open source tools. So I'll quickly go through the concrete architecture we selected because we're short on time. There's more detail of each component's and their implementation in the paper. So for our cloud monitor, we use Prometheus. It's an open source monitoring system and time series database that can collect the runtime performance metrics. So we collect metrics from the data exporter, such as Node Exporter for VMs and cAdvisor for Docker. And we stream these metrics into Drools, which we use as our state rule engine. So Drools is a business rule engine, which allows us to write when-then rules using states. The rules then send the plan to IBM Cloud Automation Manager, which is our workflow engine through CAM API. So to get all these components functioning with each other, we have to code and implement our own Java components. So you can see this in our diagram. We have classes for each component. So this leads us to research question 2. The main challenges for developing the MapeK framework from COTS is the development effort for integrating components, the monitoring and execution components with underlying cloud applications is of medium complexity, but implementing the rule engine with monitoring execution requires some effort and our own code. There's also a learning curve of some of these components. So now we'll be going through the use cases and evaluations. So for our use case, we use Acme Air, which is an e-commerce web benchmark application that uses Node.js and MongoDB. We use Docker Swarm to deploy Acme Air, and the cloud platform we use is Savvy, a community cloud provided as partnership between university, research, and industry, which is built on OpenStack. And we use EC2 cloud. So these two clouds make up our multi-cloud environment for our use case. So we apply our use cases to 3 use cases. So the first one is a self-configuration use case. We need to be able to self-configure web applications to provide good quality of service while optimizing costs. So here we deploy a 3-node Docker Swarm cluster with our Acme Air deployment. We then write the rules that must keep Acme Web and MongoDB with an acceptable threshold range. So let's go here. So these are some samples of our rules. So we have the when then statement. So in our first rule, if the CPU average is over 50% and for 30 seconds, the state rule is modified for Acme Air to be scaled. And here in our scale up rule, we call for CAM API and we modify a JSON file with a modified number of containers to scale up and send it to CAM. The next use case is our self-healing use case. So when a service goes down, we need to respawn and redeploy it. So in this use case, we support continuous deployment by maintaining good availability while potentially logging and alerting our DevOps teams. And the final use case is the hybrid cloud scaling. So here we use a key feature of CAM to allow DevOps to deploy services in a hybrid cloud setup. So in this use case, we simultaneously scale Acme Web in Savvy and MongoDB in EC2. So we have some challenges that we faced. These include deploying 2 cloud monitors with service discovery configurations for different cloud platforms and how we automated the connection of MongoDB and Acme Air. So these are challenges, and how we approach them are described in more detail in our paper. So next I'll quickly go through the results. So here are the self-configuration results. Here you can see this container is being scaled while the utilization is within the threshold. When it exceeds the threshold, more containers are deployed through our platform. Here are our self-healing use case results. So here you can see the MongoDB going down, but our framework is able to respond and self-heal the MongoDB instance. And then this is our hybrid scaling results. So here you can see the MongoDB average in the EC2 and the Acme Web and Savvy. We simultaneously deploy each of the services to keep them within the threshold. So this leads us to research question 3. So we demonstrate deployment and self-configuration in multi-cloud environments, one of the main tasks in the DevOps pipeline. We also implement self-configuration and self-optimization across multiple clouds. And the syntax of the rules for the self-adaptation use cases are accessible for both development and operation teams for DevOps. So this leads us to the conclusion. In this work, we present an industrial framework that supports automation services on multi-clouds. We detail 3 main components: the cloud monitor, the state rule engine, and the workflow engine that interact with each other based on the MAPE feedback loop. And in the future, we plan to expand our framework with support from predictive models. We plan to implement machine learning and AI models as a service to be accessible by our framework. And we want to be able to study more hybrid cloud use cases as various large industry partners are moving towards the hybrid cloud domain.